Yeah, so this is the early history of space debris activities, and history has to do with persons that sort of shaped that history, and this is a list of the most prominent persons that were active in this area. I'm going to get into more detail as we go along, but I'm starting from left to right. Left we see Don Kessler. He used to be working for Air Defense Command in the United States and later for NASA. His background is astrophysics. Next to him, his colleague at NASA JSC, Bert Cour-Palais, who was also an expert in debris matters, but also in asteroid aspects. Then Joe Loftus, he was the boss of both of them. And in fact, he was the boss of both of them. He was assistant director of NASA's Johnson Space Center. And interestingly, his background was not engineering or natural sciences. His background was psychology. And you can learn with a background in psychology, you can become a manager in the Apollo program. And that's what he was for the landing system for the Eagle. So he was a smart person, technically minded, and understood what the persons working in his hierarchy were doing. And that was important in this case. Joe Loftus also hired Nick Johnson, who became the successor of Don Kessler at JSC. Nick Johnson was a physicist from education, and he used to be working not in space, but right in the opposite direction for the submarine forces in the United States, and particularly for the atomic submarine forces, but then somehow got into space matters later. In between, he was working for Teledyne Brown Engineering and did some very important work in that field. On the European side, there was Dietrich Rex, a professor at the University of Braunschweig. He had the institute he was working at was an institute for reactor technology and spaceflight. This was combined with a view to come up with technical proposals for nuclear-powered spacecraft in low Earth orbit. Next to him is Walter Fleury. Walter Fleury was pushing the space debris issue ahead at the European Space Agency. He took over from his boss, Ernst Roth, who was initiating things in that area. So this is all you have to know about orbit mechanics. For those of you who are playing tennis, if you throw the ball for the service and you miss the ball, it's going to fall down. At the turn point, it's going to have zero velocity. Now, if you are more advanced and hit the ball, it will have a certain initial velocity. If you are strong enough and reach a velocity on the order of 7.91 kilometers a second, you will enter into an Earth orbit. You should try that. If you reach a velocity which goes beyond the orbit velocity, you will not reach a circular orbit, but an elliptic orbit. And if you are getting at velocities beyond 11.2 kilometers a second, the tennis ball is going to leave the Earth altogether on a hyperbolic orbit. Now, on the picture left bottom, you see the circular orbit and an elliptic orbit. A circular orbit is basically an orbit where we have the case 2 up above, so the ball is still falling towards the Earth, but the Earth, due to its curvature, is retreating at the same rate. And if you use the right velocity, you will form a circle around the Earth. For a little bit more speed, you get the ellipse. And for this ellipse, there are certain rules known as Kepler laws. The important one in this context is that the highest velocity is going to be at the nearest point to Earth, the so-called pericenter, and the lowest velocity at the furthest point, the so-called apocenter. If you form a line, or if you draw a line from the center of the Earth to the instantaneous position of the satellite, then within a given time interval, the area that is covered by this line is going to be the same regardless to where you are on the orbit. That's another way of saying that the momentum is conserved. So how is a launch happening? This is an illustration for an Ariane 5 launch system. First of all, you have to try to get out of the atmosphere as soon as possible because air drag is no good for launching satellites. After a while, say at 60 kilometers for the Ariane 5 case, the initial boosters, they are two solid rocket boosters named P230. They are jettisoned because any surplus mass that you have that's of no use anymore has to be discarded in order to make the launch more efficient. So then the central stage is carrying on, and at 80 kilometers it is jettisoning the fairing. The fairing protects the satellite from the impact of the incoming air due to air pressure and due to aerothermal heating. Above 80 kilometers, that's not a problem anymore, so you can get rid of that. Then a short while later, the central stage also has consumed its fuel. It's separated, and what you then have is the central 4 items that are marked there as green items, which reach the orbit. We have a lower satellite. We have a lower satellite here, and we have an upper satellite here. The lower satellite is sitting on the orbit stage that's going to perform the injection. Then there is a sort of fairing in between the satellites, which houses this one. And on top of it sits the second satellite. So for the injection, then the orbit stage is going to fire. The orbit stage is going to fire. It's first releasing the second satellite, then this one is thrown away, and then it releases the second satellite. They can also be released in different attitudes, reaching different orbits. Concerning the numbers of launches, by the middle of this year, we had more than 6,500 successful launches that led to 18,400 satellites, of which about 10,000 on orbit are still operational, and 2,500 on orbit are no more operational. They reached the end of their service time and were remaining in orbit. Altogether, we had a mass on the order of 12,000 tons on orbit. The number of satellites that you see here is just a small number with regard to the total number of satellites that we have launched since Sputnik 1. All the rest has decayed. Okay. So the topic of this is space debris. So first, maybe we have to say what space debris is. There is a definition by IADC. IADC stands for Interagency Debris Coordination Committee. That's a committee that was formed in 1993. And I think it consists of 13 or 14 members by now, and includes all major spacefaring nations worldwide. And that's an institution which was working during all crises that have happened in the political arena, and it still works today. So they define space debris as being all man-made, non-functional objects, including fragments and elements thereof, in Earth orbits or re-entering the Earth atmosphere. So I was mentioning that anything that gets into orbit has to go through a launch phase. The purpose of the launch is to release the spacecraft. Often the spacecraft is finally released by a final stage, which also remains in orbit, in a similar orbit as the spacecraft mostly. Then we have something that's called MROs, mission-related objects. That's something that's necessary to perform a mission, but which in itself does not perform a useful purpose. The picture that you see here is a cover that was protecting the optical instruments of a Meteosat satellite. And this cover of about 1 square meter in size has been regularly released in the Meteosat 1 and Meteosat 2 programs once they reach the operational geostationary orbit. Then a very important source is explosions and collisions. In the past, the most dominant contribution to the fragment population was explosions. Recently, also collisions picked up on that. Then we have some exotic sources, and as I go along, the size of these sources is going to get smaller and smaller. There was something that's called NAK droplets. NAK standing for sodium potassium. That was a liquid that was used in order to cool the reactors of so-called Buk satellites, Russian satellites that were flying in low orbits, very low orbits, so between 200, 240 kilometers altitude. And at that altitude, air drag is very strong. So if you deploy solar arrays, you come down in no time due to air drag. Hence, they built very slender spacecraft powered with a nuclear reactor. And when the mission was finished, the idea was to separate the reactor, boost it to a higher orbit of 900 to 950 kilometers circular altitude, and then let the remaining part of the spacecraft with the SAR instruments and so forth re-enter the atmosphere and do no harm during the re-entry. For the reactor itself, the reactor has a beryllium mantle, and beryllium has a very high melting temperature. So if after many hundred years, this reactor will also re-enter the atmosphere, that would be a risk. So what the Russians were then doing, they were sort of pressing out the reactor core from the reactor. And when they did that, the coolant liquid was likewise released. And the coolant was a mixture of sodium and potassium in a eutectic ratio, so that it was liquid to fairly low temperatures. And these droplets were released into space, and due to surface tension, they formed droplets. And these things were noticed fairly soon by some radars of the US Space Surveillance Network. From the decay rate of these things, they could come up with a mass which is similar to water. And from the polarization of the return echo of the radars, they could tell it's a spherical object. And when they then looked at the altitudes where these things have formed, they came up with the idea that it might be Russian nuclear reactors that were responsible for that. And within IADC, there were long discussions, and after a while, the Russians said, yes, we did release some reactor cores. In fact, they had about 30 missions of this ROSAT type. ROSAT stands for Radar Ocean Reconnaissance Satellites. So they were sort of monitoring the NATO fleets. And of these 30 satellites, 13 were releasing their reactor core. Then we also have solid rocket motor.
How much of that core was released?
How much of the in volume? It was about 30 kilograms of uranium.
Uranium?
Yes, uranium. Then solid rocket motor dust and slag. Solid rocket motors have become very important after the Challenger accident. Then the United States built something that was called inert upper stage, IUS, where it was 2 stages in one, where the major stage already had a propellant mass of about 9 tons. And in order to stabilize the combustion process, such solid rocket motors have fine grains of aluminum powder distributed over the propellant. And as these things burn during the major phase of the burn, this aluminum is oxidized, forms small particles. But once the exhaust velocity goes down, normally it's about 3 kilometers a second, as it goes down below, say, 100 meters a second, then these aluminum grains form bigger clusters. That's also due to the form of the nozzles that are used in these solid propellant rockets. And these clusters can be several centimeters in size. And at the end of the propulsion phase, when the pressure inside the propulsion module reduces, then these things escape to the nozzle to the outside. These things have been observed also by American radars, by the haystack radar. The haystack radar operates in different modes. This is a so-called beam park mode. They were looking towards the south, and when looking towards the south, they were seeing at inclinations for launches from Kennedy Space Center, which is at 28.5 degrees latitude. They were seeing objects which were related to such solid rocket motor firings. Apart from the Americans, also the Russians use solid rocket motors a lot, also for getting down their the photocassettes for the photo reconnaissance satellites. Then there is also another source, which is impact ejector. We are going to hear more about impacts later. Impact ejector are formed either by impacts from meteoroids or by impact by small debris. This is an image of the Hubble Space Telescope, where I think these fields there are separated by 4 millimeters or so. That gives you an idea of the size of the crater. The size of the crater and the depth depends first of the mass, but also on the velocity and also on the impact angle. Then we have as the last part, we have surface degradation products. So many satellites are painted with titanium color, titanium oxide colors. And these things deteriorate under ultraviolet radiation and thermal cycling when the satellite goes repeatedly through the Earth's shadow and through sunshine again. Then cracks are formed on the surface, atomic oxygen is getting behind, and then these things are released into space. Such things can be several millimeters in size to micrometers in size. So a few words about space debris history. Now that we know what space debris are, we can find a few key events that determine the history. It all starts with the launch of Sputnik 1, where also the first debris was produced, because the Vostok stage, once Sputnik was injected into the orbit, the upper stage of Vostok was also left in almost the same orbit. And Vostok, the orbital stage, also became the first uncontrolled re-entry on December 1st, 57. It fell down over the Caribbean. In 1961, we had the first on-orbit explosion. That was the explosion of the orbital stage of a Thor Evolstar rocket that transported Transit 4A and 2 other satellites into an orbit of about 700 by 800 kilometers altitude. And about 1 hour after the injection of the satellite, the orbital stage of the Thor Evolstar exploded. And instantaneously, within fractions of a second, it more than tripled the existing on-orbit debris population. That was the most severe single increase, single relative increase of the orbit population of all times. At that time, we had about 120 catalog objects only, and the explosion generated another like 350 or so. Then in '64, we had the first satellite injection into a geosynchronous orbit, SYNCOM-3. I think that was used to transmit some TV broadcasting from the Olympic Games in Rome. Then in '86, we had the first, if you like, successful anti-satellite test, where the Russians first launched Cosmos 248, and then thereafter another equivalent satellite, Cosmos 249. They did a rendezvous maneuver getting Cosmos 249 close to his predecessor, and then they blew that satellite up, and the fragments of 249 was then destroying 248. So that, in their view, was a successful ASAT test. In '78, we had the first explosion of a geosynchronous satellite on orbit. That was the Russian Ekran-2. In '58, we had a first anti-satellite test from the ground, if you like. There was a satellite of the United States by the name of Solwind that was reaching its end of life, and it was decided to use this to check out the abilities of the Air Force to destroy a satellite by a missile that's launched from a combat aircraft. This was happening, the intercept was happening over California, as Solwind was on a northward path towards Alaska. And the cloud that was generated due to this successful intercept could then be viewed by two radars in Alaska. And that also helped to later verify explosion and collision models and fragment generation routines.
What was the orbit of ASAT?
They used Solwind because it was already at a very low altitude. They did that because they were environment conscious. We are going to talk about how that works later. The orbit was below 400 kilometers or so. And that means anything that's generated in terms of fragments is going to be down within a few months. Then in 1986, November 13, I even believe it was a Friday, the first European in-orbit explosion was happening. It was an Ariane 1 H8 orbital stage that blew up on a northward pass over Africa. We are coming to that in more detail in the next few graphs. In 1996, there was the first confirmed in-orbit collision where a fragment of this Ariane explosion was hitting the gravity gradient boom of the Ceres satellite. Ceres was an French defense payload that listened into radio communication on ground. And it was, in its attitude, stabilized by a gravity gradient boom where the satellite here is, then there is a mass down there, and then there's a long boom. And due to the change of Earth gravity, it changes just slightly over a few meters, but it does change. Anything that has this sort of shape with two masses at the end of a line, anything like that will stabilize in a mode that it points radially to the center of the Earth. So that mechanism was used for the stabilization, and that boom was severed. They could tell that Cerise, I think it was like 3 meters. This I can't tell you in detail because it was a defense payload. So, but I think, yeah, this is just the only illustration I could find. I couldn't tell the artist to redo it. Yeah. So.
But the gradient, gravitational gradient stabilization, it must be really tricky business.
No, it's very simple.
Well, it's simple, but I mean, it's very tiny.
It's tiny, but it's there, and it's long lasting. It doesn't cost you any energy.
That's fine.
I guess if you want to take a high resolution picture on the ground, you want to avoid any macro aberrations, you want to avoid the blurring picture. So with the gravity gradient, you don't have any mechanisms.
Yeah.
The picture, so you just pointing on one.
There's
some satellite rotation of the Earth.
Because in the early stage of our satellite, I was thinking of the gravitational gradient.
Yeah.
But I mean, I said, well,
but you know, we have a very good example that everyone can view at night. The moon is in a gravity gradient mode. That's why we always see the same part of it. Yeah. Yeah, there are some pictures illustrating all what I have said so far. In fact, at least in Europe, space debris came to our attention due to re-entries. At the beginning of the 1970s, the last Saturn V launch was used to put Skylab into orbit. Skylab had a mass of about 78 tons, and there were 2 crews that were doing work on board Skylab, but then thereafter it was left stranded in an orbit of about 400 kilometers or so pretty similar to the ISS orbit. And unfortunately, the fuel for maneuvering the spacecraft was not sufficient to come up with a fully controlled re-entry. So a very steep re-entry into an ocean area where no one lives, this could not be done anymore with the fuel available. But what the Americans did do is they used attitude control thrusters to change the air drag of the spacecraft. So there are different attitudes. There was what they call a wind-milling mode where it was going like that, and then there was a low drag mode where it was going like that. And with this control of the drag, they could, in the long term, plan where it's going to fall down, or first of all, when it's going to fall down. And when you know when it's going to fall down, then you can determine on which ground track it's going to fall down. So it has about 15 ground tracks per day, which are then separated in terms of longitude. And once you have established the correct day, then you try to shift to the ground track, which has the lowest casualty probability for the population that's living underneath that ground track. And they came up with an orbit which has that probability, that property. And that orbit was going across the United States, over the Atlantic, the Indian Ocean, Australia, the Pacific, and then United States again. Of course, they didn't want it on the United States. So the final thing they did is they used a final thrust. In fact, if they wouldn't have done anything, it would have fallen down over the United States. So the final thing they did was a change in attitude again in the low drag mode so that it overshot the United States and fell down half an orbit later, where unfortunately Australia is. So Americans were happy, Australians were not. And they tried to get it down over the Indian Ocean, but many parts of it reached the Australian continent, and you can see the trace and sizable objects, some of hundreds of kilograms were found on the ground.
Do you know what type of the spacecraft survived the entry?
Yeah. Yeah, there are like film cassettes, docking ports, things of that sort. They survived. So that was that one. Yeah, on top of that, very first bullet, in 1978, we had also a re-entry that was, again, by one of these ROSATs, these ocean reconnaissance satellites, Cosmos 954. That had malfunctioned and came down over Canada's Northwest Territory, and it was spreading its breakup fragments and also radioactive material along a long swath between Yellowknife and Hudson Bay. So the Canadians, that was in the middle of winter, so the Canadians had quite some trouble to collect the fragments from the ground, and they were also issuing then an invoice to the Russians, who finally paid. Then on the bottom, we have in 1983 another ROSAT, Cosmos 1402. In contrast to the one in 78, in this case, the separation between the payload and the reactor was working well. Normally, they do a separation of these two, and then the reactor with the propulsion module is raised to an orbit of 900 to 950 kilometers circular. The separation worked, but the reboost to that higher orbit did not work. So both things fell down separately, and one of them came down over the Atlantic. That was the reactor, and a lighter weight part with the payload fell down over the Indian Ocean.
Why do you want to do those of the separation?
So they separate the payload from the reactor, and the reactor has a booster connected to it, and then they boost the reactor to a higher orbit. And the question is, why do they do that? Because of the decay rate of the uranium on board. Because in orbits like 900 to 950 kilometers, you have lifetimes of several hundred, if not 1,000 years. And that means once the reactor is switched off, the decay rate will be much less. Okay. Yeah, there were some reactions to these high-risk re-entries. First of all, technical capabilities were improved, worldwide, you can say, but particularly in the USA and USSR, and also in Germany. I mentioned Professor Rex in my very first slide, who got involved because of his Institute of Reactor and Spaceflight Technology. That was in context with his ROSATs. But also France, Italy, UK, and ESA did something in that respect. For risk mitigation, I mentioned that NASA did a controlled, sort of semi-controlled re-entry of Skylab with a controlled decay rate, so that the final orbit had a nodal longitude, which led to a minimum risk of casualties along the ground track. Then in 1979, there were UN principles established at UN COPUOS. UN COPUOS stands for United Nations Committee on the Peaceful Uses of Outer Space. And the forum that did that was the Scientific and Technical Subcommittee. They formed a working group on nuclear power sources, where Professor Rex was a member. And then they came up with a catalog of principles that later became principles relevant to the use of nuclear reactor power sources in outer space. which then was also known as the Rex report. Then we have the UN Liability Convention. This convention existed, and it was first called upon when Cosmos 954 re-entered over Canada, when Canada claimed compensation. I think they claimed maybe 6-7 million, and they got 3 million, which was already some progress in that matter. Also, the USSR modified the design of their ROSATs to make them more reliable, and in fact, that was important because there was another ROSAT which was called Cosmos 1900. For Cosmos 1900, nothing seemed to work. It didn't seem to communicate with ground station anymore, so the satellite fell down in one piece with the reactor and its propulsion module and the payload all together. But apparently in the meantime, they had built in an automated process where the satellite is sensing in what altitude it is, and when it reaches a certain critical altitude, it has an onboard automatic program that's run, and with this automatic program, that separation was performed, and the reactor was still propelled to a higher orbit. Since it was so deep in the atmosphere, the orbit was not 900, 950 kilometers, but more 700 kilometers. On-orbit explosions were a dominating contributor to the space debris population. I mentioned earlier the Store-Able-Star explosion in an orbit between 880 and 1,000 kilometers in altitude at an inclination of 66.8 degrees. Inclination is also important for the global distribution of the fragments. From this event, almost 300 fragments were catalogued, and I mentioned before that was increasing the population by a factor of 3.5. Then in 1975 to 81, NASA performed an analysis on the space surveillance catalog that they had, and they noted that there were several distinct events generating a population of fragments, and of course the best assumption that they initially had was it was due to the Russians, but that was not the case. It turned out that it was 8 delta orbital stages that were exploding, and they at that time were responsible for an increase of 27% of the tracked population. We are going to see in a while what they did to resolve that problem. Then in '86, we had this Ariane H8 orbital stage explosion that was on an orbit 800 by 830 kilometers at a synchronous inclination of 98.7 degrees. That was after Spot 1 was delivered into orbit 9 months before. And this fragmentation created almost 500 fragments, which was the worst breakup until 1996. And it increased the population at that time by 7%. You can see the events are marked with 1, 2, 3, and you can see them in these diagrams where we see number of fragmentation events. So in top times we had even more than 10 fragmentation events. So this is the Able Star. These are the delta fragmentation, and this is the Ariane fragmentation. And you can see in the number of objects versus the time axis, you can also see that there are bumps in the history of the catalog population, which otherwise is more smooth.
Could you please remind us what then are all these?
Mission-related objects. Okay. Yeah, so when we have an explosion, what happens? This is an illustration of what's happening. This is, in fact, an illustration, a simulation of the Ariane H8 fragmentation. it fragmented as the satellite was flying over Africa on a northbound orbit, going towards East Europe. Yeah, in fact, the fragments were first seen via radar in Turkey. I think we are coming to that in the next presentation. So after such a fragmentation, you can assume that there is a delta V, a change in velocity imparted on all the produced fragments. And the velocity distribution you can assume homogeneous over a sphere. But the relative velocity from such explosions is on the order of maybe 400 meters a second. The orbit velocity is 20 times higher than that. So even these 400 meters a second do not have a high impact on the change of the orbit inclination. They just have a noticeable effect on the velocity along track. So for the velocity along track, there are some particles that are decelerated, where the additional velocity goes opposite to the direction of motion, and some of them are receiving a higher velocity, and that goes into the forward direction. For the ones who receive a higher velocity, they reach a higher orbit. So this is after one orbit. You see these things here reach a higher orbit. There have been some that reach a lower orbit, but those who reach a lower orbit have reached an orbit that was so low that the nearest point to Earth was below the Earth's surface, which means that they decayed immediately. What you can also see there, that's something up here. That's a very thin part of the cloud. That's super pinch point. So when you impose a delta V on an orbit, you can change all sorts of things, but all new existing orbits will pass through that very point again. That's this pinch point. You see, after 20 orbits, we still have this pinch point, but there is a whole series of new orbits here. And when you wait long enough, after 3 months, then also there is an effect on the orbit plane. And the fragment orbit planes are going to rotate. This is due to Earth oblateness and air drag to some extent. Yep. Now, the effects that we've seen before have been used by someone.
By the way, out of total mass of exploding spacecraft, how much stays in the orbit? Because some directly go into the atmosphere.
Yeah, it depends on the orbit. If you have something in geostationary orbits, everything would remain.
Yeah.
Yeah. So the principles that I've illustrated on the previous slide have been used by a guy named John Gabbard. He was from NORAD, North American Air Defense Command. And this guy was just throwing all the data of the catalog into his computer and plotting the data of the different orbits with their perigee and apogee altitude against the orbit period. And when he did that, then he was noting diagrams which looked like the one on the left-hand side, such an X-shaped diagram. So the idea here is that this is the initial circular orbit, and when we apply the delta V, then some things are decelerated, and the decelerated ones, in order to go to the same pinch point, still have the same apogee, but have a lower perigee. Same apogee, lower perigee. Those that are accelerated maintain the perigee and have a higher apogee. Now, if you wait long enough, then due to air drag, because this is altitude, and with decreasing altitude, air drag decreases. Due to air drag, the further you go down, the stronger the effect of air drag is. And these points, initially from there, and that was down. Once the So after a while, the left-hand side of this X-shaped diagram is collapsing, and thus the right-hand side is surviving. So this sort of illustration is was later named the Gabbard diagram, and that's a distinct footprint of any fragmentation event. Yeah, reactions to on-orbit explosions. For the Able star orbit stage, nothing really happened as far as design is concerned. We just noticed some more details on the fragmentation event itself. For the Delta II orbit stages, the probable cause was a rupture of the common bulkhead of the fuel oxidizer tanks, which were of hypergolic type. That means when they mix, they will by themselves explode. The common bulkhead has most likely ruptured due to overpressurization caused by solar heating. So McDonnell Douglas introduced a venting of the oxidizer tank after the payload release in 1981. And then thereafter, there were no more explosions reported from Delta H2 orbital stages. For Ariane, the H8 explosion, as so often, the first people who noticed that were the people in the United States from the Space Surveillance Network. At that time, they had a contributing radar sensor of the Space Surveillance Network at Hirinclik in Turkey. And as I said, the explosion was happening over Africa on a northbound path. And that was directly flying over this radar. And that radar saw immediately a big cloud of fragments. At that time, Nicholas Johnson was still working for Teledyne Brown and working for the US Space Command. And one day after the event, he informed Don Kessler at NASA, who was the main expert on debris in NASA. He contacted Joe Loftus, who was the boss of his boss. And Joe Loftus passed that message to NASA headquarters, and it just so happened that the ESA DG was talking to the NASA administrator at that time. So that was a rare coincidence, and that then immediately led to ESA calling in an industrial team to take actions and remedy the cause of this breakup. And they implemented mitigation measures by venting pressurants and propellants as of the launch number 35. The event was happening on launch number 16. Then thereafter, there were no reported explosions of these H8 or the similar H10 orbital stages anymore.
So we got one question. In the 60s, American military has made one experiment. They have initiated in upper orbit one nuclear explosion, which was in the orbit known as third 1 hour belt for 50 years. Do you have some information how this event have had influence on the reentry of satellites in geostation?
At that time, there was not much to destroy, but I don't have information.
I have information because I prepared for a talk recently. So at the time, there were, I don't remember, around 100 satellites. It destroyed 1/3 of the satellites. One third, mainly because there was radiation, excess radiation, and the radiation impacted mostly the solar panels, and that degraded the lifetime of the satellites. So the first commercial communication satellite was destroyed. The first UK satellite was destroyed. So this is the case.
Thank you very much for this information.
Yeah, I talked so far about explosions, but collisions are going to become a more serious problem in the future. In fact, they are set to be dominating the environment in the future. This shows a few examples. I was already mentioning series where the gravity gradient boom was fragmented. It was severed by a fragment of an Ariane H8 explosion. At that time, just one additional object was detected. I didn't mention that before. That was also done in Germany, the observation of that spacecraft on request of CNES, where the German, at that time, Afghan radar, they have an imaging capability in Ku band, and they detected the former satellite major payload and the severed part of the gravity gradient boom in their radar. So you could clearly say that there was a kinetic event severing this boom. Then there was an intercept by a Dongfeng medium-range missile acting on Fengchun 1C. That was in January 2007. From this event, we had almost 3,500 additional catalog objects, which was increasing the catalog size at that time by about 38%. Then we had the first, if you like, serious in-orbit collision between two satellites, which was between Iridium 33 and Cosmos 2251. That was in February 2009, happening over Siberia. And this event generated almost 2,300 additional catalog objects, increasing the size of the catalog by about 20%. And you can see the jump in the object counts in this diagram. See between 1960 and 2000, things are fairly smooth. You can see some ups and downs. These ups and downs are often related to the solar cycle because air density increases at higher altitudes and things tend to decay more rapidly. But then you have this step function there due to these two Fengchun 1C and Iridium Cosmos events. On the right-hand side, you see a simulation of the generated clouds. So the event was happening over Siberia, and again, we have such a pinch point. Everything was going to the point of the initial collision. They are not going to this point all at the same time, but everyone is going to that point again. And I mentioned that fragmentations due to collisions are going to dominate the environment in the future. Yeah, why are we worried about fragmentations? I guess you are going to hear much more about that in the presentation on hypervelocity impacts. We are worried because a 1 centimeter object that was used to impact a solid aluminium block on the left-hand side. So the aluminium block was about 10 centimeter high, and the impacting particle was a sphere, aluminium sphere of about 1 centimeter in diameter. And the impact was happening at, I think it was something like 6 or so kilometers a second. And you see what the effect is. When you experience, you can get all sorts of effects, and this is one effect that's very, very noticeable. So first of all, you see that such an object, this of course is a replicate, the original object is gone. First of all, you find that the aluminium is molten, and the molten part is going to be expelled into the outside. But some of this is solidifying and forming a crater rim up there. But then there is a shock wave running through the material, and the velocity with which the particle impacts is in fact higher than the velocity of sound in the material itself. So this thing is going through the material, and since the material properties change from aluminium to air, the shock waves are reflected on the back and then overlaid by forthcoming waves from the front, and that then rips this thing apart. It's a very expensive way of creating a perfect vacuum. Well, this is just inside with no opening to the outside world. Yeah, so such an impact is equivalent to the kinetic energy that's generated by a mid-sized car that runs into a solid wall at 55 kilometers an hour, and it's equivalent to the explosion of a hand grenade. So this was a 1 centimeter object. We can assume that we have about 1,100,000 of those. The International Space Station, in fact, has been designed to protect it against particles between 1 centimeter and 1.2 centimeters, depending on the modules you're looking at, in order to protect the personnel on board. This is happening by means of so-called Whipple shields, or stuffed Whipple shields. There are 10 centimeter objects, of which we have about 40,500, and if we have an impact with such a thing, then we can assume that we have a total destruction and breakup of a spacecraft or orbital stage. 10 centimeters is the operational detection limit of the space surveillance network radars. Some of them can do better, but on the average 10 centimeters. Also, already 1 millimeter objects can do damage, and we assume to have about 130 million of those. If they hit cabling, electronics, optics, they can do severe damage to a spacecraft already. Yeah, and this is what is done for the shielding, just to illustrate the Whipple shield concept. So Fred Whipple came up with that concept already at the end of the 1940s. He used at that time a 2-layer hypervelocity impact shield. The idea, and I should say that these images have been generated by Hans-Martin Institute, also the previous one, and we are going to hear more of the Hans-Martin Institute that is never updated. So the principle is we have an object coming from this direction, which is hitting an aluminium surface here. It doesn't have to be very thick, just 1 or 2 millimeters. When it hits this surface, the impacting object is going to be fragmented. Some of it is vaporized, some of it is liquefied, and it then generates a cloud of fragments, and the cloud of fragments is then later, at a distance of about 10 centimeters of the field, distributed over a wider surface. So the surface pressure here is much less than up here, and this vacuum can withstand the impact. And this is what such a cloud looks like when you have a high-speed camera taking a picture of it. And on the right-hand side, you see the implementation of such a shield for the International Space Station around the problem. Nowadays, they don't just use this original Whipple shield, but they are stuffing it with fabrics of Kevlar and Hexter that further slows down the velocity of these particles and makes the protection even more efficient. So how probable is it to have an impact by such objects? We used this MASTER model. MASTER stands for Meteoroid and Space-Debris Terrestrial Environment Reference. That's an ESA environment model on space debris. We used it for a sun-synchronous satellite at 800 kilometers with assumed 10 square meter cross-section, and we are going to have, for objects larger than 1 millimeter, we are going to have about 1 impact in 5 years, most likely by debris. But also there's a 1 in 4 chance to have an impact by meteorites as well. There's a chance of 1 in 330 years for objects larger than 1 centimeter, almost exclusively debris, and a chance of 1 in 6,000 years for objects larger than 10 centimeters, and that would be exclusively debris. statistically speaking. So I'm going to say something about the technical exchange in debris matters. There was a publication by von Kessler on derivation of collision probability between orbiting objects, the lifetime of Jupiter's outer moons. But this inspired him later to do research on what debris do in Earth orbits based on the same analysis principles. In 81, there was the first position paper written by American Institute of Aeronautics and Astronautics. In 82, there was the first dedicated conference on orbital debris organized by NASA. In 84, there was the first international workshop on space debris at the 25th Coast Bar in Graz. Then in 86, there was the first dedicated space debris session at Coast Bar 26 in Toulouse. In 87, we had the first book on artificial space debris by Nicholas Johnson and Darren McKnight. 88, we had a report by the ESA Space Debris Working Group on space debris. A year later, we had an equivalent report by the US Interagency Group Space. In 91, there was a publication, another one by Don Kessler, where he talked about collisional cascading in low Earth orbits. And the idea he came up with was that the spatial object density in some orbit regions is so high that even if you instantaneously stop any launches, the mass that's already in orbit is sufficient to generate a runaway collision situation. In 93, we had the first European conference on space debris at ESA. In 1993, we had also the founding of the Interagency Space Debris Coordination Committee, where NASA, Russian Space Agency, NASA, and ESA were founding members. In 93, we had a position paper on orbital debris by International Academy of Astronautics, and since 1994, space debris has been a UN COPOA's agenda item at the Scientific and Technical Subcommittee. So I can say that space debris has, in more than 40 years, become a recognized research item, and it has become an integral part in the design, manufacture, operation, and safe disposal of space systems. The identification of space debris as a global risk for manned and robotic spaceflight and the early initiatives for international operation to mitigate consequences go back to just a small number of colleagues, and most of those were listed on the very first page. And today, space debris can be regarded as an important accepted research item, which, as I mentioned at the beginning of this session, have top-ranking statistics in technical sessions at IAC and COSPA. And if you want to get into more detail, there's some recommended reading that you can find on. Thank you very much.
Okay.